Okay, in this video, I'm going to start introducing functions. And presumably you have seen functions before, but we want to be very careful about the definition here. So I'm going to define them from scratch. And in part, we want to be very careful about the definitions because we're going to want to prove things about functions once we get some more to work with. And so let's see, given a pair of sets, um, assume that for each x in A, there is associated a unique element of B, which we denote by f of x. Then f is said to be a function from A to B denoted and if you've again, I'm sure you've seen functions before, or it's not unlikely that you have, but you may not have ever used this notation, which is very important in upper level mathematics, where we want to show explicitly, we define a function or we introduce a function with some name, and we tell you what the domain and what's going to be called the codomain are right away. So now A is called the domain. B is the codomain, and set of all images under F for points in the domain is called the range. Okay, so here is a very careful, perhaps a bit wordy definition of what a function is. For each element in the domain, there is a corresponding element in the codomain. And so let's just look at an example here. So it's going to be very common when we want to look at these functions now to draw them as like sets like this, maybe. So here's A, and then the codomain will also be a set B. And, I could label these things. And then F is an assignment for everything in the domain to something in the codomain. So maybe something like this. Okay, so we know that, or we notice already in this example, so everything in the domain has a corresponding image in the range. There's an arrow associated to this where we go left to right in the picture that doesn't go backwards in this picture. Though I won't draw the arrows, I'm just saying that anytime I draw a function like this, it's always going from left to right. And we notice that, of course, multiple elements in the domain could be sent to the same element in the range, and we'll talk about that. Or sorry, the same element in the codomain or the range. And So what's the range of this function? So the range of f in this case is, well, in this case, it's all of b, right? But let's just write it like this. So 2, 5, 9, and 11, which is actually equal to b in this case. Okay, let's look at some more examples building on what's going on here. So even if you feel very confident about this definition, I want you to get used to the different setting and the different way that we might be expressing functions than what you're used to in calculus. In calculus, we basically always graph functions on the xy axis. Nothing wrong with that. But when we get into higher level mathematics, we sometimes do not want to do that anymore, or we are not even able to do that anymore. And we want to instead visualize the domain and the range, or the domain and the codomain separately as a map like this from one to the other. So it's helpful, I think, to look at an example which you've already seen in calculus, like absolute value of x, for instance, and think about how you would visualize it in this new method. Now, I can't draw the entire real line, but I'm going to just kind of do the best I can to visualize this. So you can imagine here is a copy of the real line. And of course, it goes up forever and then down forever. And -1, -2, -3, -4, -5. Just to give us something to work with here to visualize. And then on the other side, the the codomain is the same thing. So okay, and the way that we can draw this function now is, again, we want to say, well, 0 goes to 0, 1 goes to 1. The positive part is kind of boring, right? Just kind of, and notice I can't draw these lines for every single real number. I would it would ruin the picture. So I'm only going to do it for the integers, even though it's defined for every real number, just to get the idea. And -1 will be sent to 1, -2 sent to 2, -3 sent to 3, -4 sent to 4, and -5 sent to 5. So what you imagine here is that you take the real line and you're folding it over on itself in this picture, right? So that's what's going on. If I imagine this function is going from the domain to the codomain, visualize it that way, I fold over the real line, and the crease when I fold it is at 0, right? Is how this is worked. Okay, great. So what's the range of f then? Right. So the um, range of f is well, including 0 all the way up to infinity, which of course is a subset of the real numbers. Okay, good. And then just to, of course, you're used to graphing this function on the xy plane, and that you would graph it this way. But again, when you graph it this way, notice that the domain is on the x-axis and the codomain is on the y-axis, and then we graph in between on the xy plane. But we can still think about what's happening for the function going from the domain to the codomain. And here we also see that what the graph is suggesting is that we are folding over the domain onto the positive y-axis. Okay, so now when you introduce a definition of something, you should also give examples of things that violate the definition. So that's what I want to do now. Give some very simple examples of things that are not functions, right? So here, I want to be clear, we give two non-examples of, meaning that they are not functions, right? So for one, if you, just to give something really simple, if I have something like this, I can still draw it, but this won't be considered a function. And if I just say that, maybe 1 gets sent to 2, 2 gets sent to 3, and then I stop, then this is not a function because there's no value for f of 3, right? So um, there is no value for f of 3. So it's not a function. And okay, that's one way. You just don't define what the function does for a particular value of the domain. Another way is you um, define sort of too many things for the domain. What do I mean by that? So 1, 2, 3, 1, 2, 3. What if you send 1 to 1 and 1 to 2? And you send 2 to 3 and you send 3 to 1. Everything's fine except for the fact that you sent 1 in the domain to 2 different values in the range. Um, that's not okay. So you're not allowed to do that. So there are values defined for f of 1. So that's not okay. Okay, so those are the kinds of things that we don't want to allow if we're going to talk about functions. All right. And the second example that I did is actually related to something you've seen before, I don't know, at some point in your math career, where if you graph a circle in the XY plane, then we say in the XY plane, there's something you've probably heard of before called the vertical line test, where if you like have a graph and you look at the vertical line and it crosses it twice, then it's not a function, right? But the reason why that is because there's some value in the domain so that it's getting sent to 2 different values in the codomain, and that's not a function, right? So it's the same kind of thing as what I'm explaining in this second picture going from a domain to a codomain, right? Okay, all right, let's do something with this definition because we don't want to spend too much time beating a dead horse here. So we want to define some further properties because oftentimes we're not just going to study general functions. We'll almost never do that. We're going to have some property of the function. And depending on what class you're in, you're going to have a lot of properties of the function. So it depends on what you're doing. But we're going to stick to like just kind of set theory facts about functions. So we're going to impose actually quite little on the functions, but we do need to give some properties. So the first one is we're going to study injective functions. So this is a function from A to B is injective, or 1 to 1 is what we often say, right? So or 1 to 1, which is like the more informal but common thing to say. If the image of 2 different values is the same, then that implies that actually the values in the domain must have been the same. So the only way you can get the same output in the codomain is if you started with the same input. Okay, good. So that's a definition. And I just want to below this write this in more like in the quantified language. So um, for all A1, A2 in A, if f of A1 equals f of A2, then A1 equals A2. Okay, it's helpful to have it in this sort of more succinct, quantified way of writing this down. And so let's look at some examples, right? So here are some examples. So first of all, if I take function like this, so starts at 1, 2, 3, going to a codomain with 4 elements, and f is going to do this following thing. So 1 will get sent to 2, 2 will get sent to 4, and 3 will get sent to 1. And it doesn't matter that I missed something in the codomain. The fact is that every element in the domain gets sent to a unique element in the codomain. There's no duplicates in the codomain. So this is injective, right? Um, so this is an injection. And then to just be clear, we can do another example right here which will not be considered an injection. So now I'm going to send 1 to 2, 2 to 4, and 3 to 2. And this is not an injection because there are 2 different values in the domain that get sent to 2, right? Okay, so we're going to want to prove things about functions being injective or not injective. So in order to prove that it's injective, we have to satisfy this definition. So you may ask, like, how do I prove if it's not injective, right? So here we can note that by considering the contrapositive to this definition, um, well, sorry, the contrapositive is going to give me something equivalent. So this is a different no, sorry, but so by considering the contrapositive, the definition 8.3, we find an equivalent definition, which is that if A1 is not equal to A2, then f of A1 is not equal to f of A2. Good. We will talk about how to prove something's not injective later when I go to prove things. So for now, I will leave that out. Okay, so what else are important things to define about functions? Well, the other thing that we often want to define is what's called the surjection or onto. So a function is surjective or onto if for every b in the codomain there exists some a so that f of a equals b. Okay, so that's the definition of a surjection. And again, in this more quantified way, I could say for all, so I could say for all b in b, there exists an a in a such that f of a equals b. Okay, so everything in the codomain needs to be hit by some image under the function. All right, let me give myself a little bit more room here. And now we just want to look at an example that is a surjection and one that isn't, right? So just to make sure you understand what this is getting at. So I'm just going to draw these two different examples, similar to what I did for injection. So let's see, 1, 2, 3, 4, 5. 1, 2, 3, 2, 3, 4. 1, 2, 3. So the first one will be uh, a surjection. So we're going to send, there's a lot of different things I can do here. So this is surjective. And of course, it's surjective because everything in the codomain gets hit by something from the domain. But this is clearly not one-to-one because 1 and 3 get sent to 2 and 2 and 4 get sent to 1. So it's not a one-to-one function. But right now, we're not talking about injective functions. We're just talking about surjections for a second. So here I'll send 1 and 2 to 1, and I'll send 3 and 4 to 3. And so this is not surjective, right? Because nobody gets sent to 2 in the codomain. Okay, simple enough. Again, we'll get more practices with this when we go to prove that things are surjectants or injections or not, either of those things. But for now, I'm just defining them. So we'll get more practice with this. And then there's one more definition that we want here. So we say that a function is bijective if it is both injective and surjective. Okay, so this is basically, it's a definition where we just combine two other definitions, but it's very important. So a bijection is going to be really important because it will preserve the cardinality of sets. I haven't really talked about cardinality of sets yet, but it'll preserve it means that the domain and the range will have the same size. And if they're finite sets, then literally just, if the domain has 4 elements and it's a bijection, then the codomain will have to have 4 elements. But it'll be very important for defining sizes of infinite sets as well, where we don't really have a good notion of what the size of an infinite set is until we introduce bijections. Okay, so let's just look at an example of something that is a bijection. And if you followed what I just said, that means that if I'm going to give you an example of something that is a bijection, the domain and the codomain have to have the same size. So that I have to make sure I set that up right away if I'm going to try to give an example. And so here we go. I'm setting that up. And now I can send, well, there's lots of choices here, but let's just see. I got to send everything, got to hit everything, and not twice. Okay, so this is a bijection. And this gets studied in algebra too, because you can study permutations now. You can think about these bijections as just permuting the elements of a finite set. And it turns out that if you compose permutations, you get a group, and it has nice algebraic structure. So these things will show up in various different places depending on what you're studying. In set theory, bijections are important to study cardinality of sets. And they show up in almost every area of mathematics because we want some way of preserving a structure. And at the very least, you need to preserve the cardinality. So you'll usually impose a bijection, but you'll also impose other restrictions in order to preserve the algebraic structure or the topological structure or the analytic structure, whatever it is you're studying. So bijections will show up all over the place in mathematics. And as we continue to study them in the next videos, we're going to learn to prove that things are injective, are surjective, and or not injective and not surjective. So we'll practice proving those things in both possible combinations.